Yes, sir. We are live on YouTube as well as on Zoom. Good evening, participants. Welcome to the live session for the course Oscillation Wave and Director Vibration in a Continuous Media. Our instructor, Prof.Avijit K. Ganguly, sir, is with us. So let's begin, sir. So we invited the students to join on Zoom. So far, nobody has joined. Maybe we'll wait for a minute or two, sir.
Thank you, Sir Murli, for
Yes,
your
sir.
production.
Your voice is too low, sir.
Yeah, now is it better?
Yes, yes, sir.
Yeah, thank you for your nice introduction.
You're welcome, sir.
I hope that this live instruction, your live session, will be useful for the participants, and in turn it will help us, the instructors and the people who have been assisting me for all these ways.
Nice. Dr. Ankur will also be joining the session, sir?
Yes, Dr. Ankur is here.
Okay, sir.
He'll just, in a second, he will be streaming with me.
Great, sir. Meantime, I will just check whether students are watching the event on YouTube. Just a second, sir. I'll just check. Dr. Ankur.
Here is Professor Ankur.
Hello, sir. Good afternoon, sir. Yeah. So far, no one has turned out. Sir, in the meantime, would you like to discuss on the content that was released so far? I think till 5th week, we have released the course content.
Yeah.
Would you like to briefly discuss?
I'll try to give the background of this session.
Definitely, sir.
What drove me to think of delivering this set of lectures was the fact that most of us during our undergraduate or postgraduate days study this oscillation wave and its propagation in a standalone manner. And when we join research and this particular topic comes up and it is used for finding out various physical conditions of the sources, then there are several key aspects. Those remain unfocused, rather, they are not taken into consideration. So what drove me to think about this particular aspect was the fact that maybe I'm actually estimating certain parameters based on one particular effect, but it's not just a one particular effect that gives rise to the numbers that I see on my screen. There may be multiple factors, those are associated with it. So how do we actually take those corrections that are coming from various sources to my result so that the basic picture or the basic aspect of the physics that's being taken into account is not going to be misinterpreted. So that's what drove us together to look into this aspect. Me and Dr. Ankur Chobe, we have been looking into certain physical phenomena and some kind of, what do you say, electromagnetic spectrum that's we are receiving from the stars. And based on what we see in our apparatus, based on the numbers, those are generated from there, we try to ascribe certain physical conditions that's prevailing at the site of origin of this electromagnetic radiation. But it so happens that if most of the time the celestial objects are in motion The motion can be translational motion, there can be rotational motion, there can be various other aspects, distortion due to presence of gravitational field. So in this background, when an electromagnetic wave propagates, they get affected. And that finally results in change in the numbers that we are going to register in our notebook from the devices. So in principle, there should be several measurements, those take place. Each one of these measurements should look into different aspects of the corrections those are coming. And once any particular number or any particular observation, set of observation, those have been undergone or those have been considered, one should apply these corrections one after another over there. And then after applying these corrections, they should decide about the physical origin of these radiations. And finally, from this analysis, one can go to decipher about the fundamental constituents of the nature as well as stars or compact objects or supernova and things like those. So this is in general the background that played a major role in chalking out this particular course. So what we did during this particular set of deliberation, we leaned heavily on few aesthetic aspects of physics. Those come from, say, group theory. Those come from quantum field theory. And those come from the equations those are solved using various formulas of differential equations. So we made use of them and also made use of few other known aspects, like one of them are Stokes parameters. Those have become an indispensable tool for finding out the spectropolarimetric features or spectropolarimetric analysis of the star of the light those are received from the stars, and how these particular observations of Stokes parameters or this data undergoes modification because of various physical situations those are prevailing at the source, or the source itself is having undergoing such phenomena, like it can be moving towards us at a certain speed, it can be rotating and things like those. On the top of it, the in situ material inside that source that may be in very, very highly hot, and the temperature over there may be large. So because of the temperature over there, the constituents may change from one form to the other. The character of the distributions and the other things like the mass of the particles those are involved in making up the medium, they undergo a lot of changes. So when you take those into account, you can see that a medium that may resemble like a classical medium for somebody, when this is moving with a speed which is comparable to that of light, then it might appear to be different. So before coming to a conclusion about the nature of the source, one should make sure that whether this particular system that is under consideration is stationary with respect in a particular frame or it's moving. And once these aspects are clear and has been taken into account properly, then any conclusion about the constituents of the source would turn out to be rather error-free. So this was something that has motivated us to look into this aspect and deliver the contents in a compact form that one can go through in a little smaller period of time. And then if they find it interesting, it's applicable for their studies, then they can dig into it and elaborate studies they can undertake and use them subsequently to come to the right conclusion. So that's in short what had driven us to this conclusion. To provide you with an example, probably most of us, including all of us present on this side of the screen or the other side of the screen, we are familiar with something called Faraday rotation or Faraday effect that electromagnetic fields undergo when they pass through a medium which is having some finite density of material, matter, and magnetic field. Generally, there is a tendency among the practitioners, and the tendency is to treat this particular effect as an ad hoc effect on the top of the other effects that perturb the electromagnetic spectrum usually, or its propagation. It was quite some time back that we had shown and demonstrated that depending on certain parameters, this particular approach may have its limitations, and it may not be appropriate to treat at all ranges of frequencies and materials and densities this particular effect to be as an ad hoc effect. So it was something similar in continuation to that. The earlier one was, that one just spoke, was essentially something that was written for journal readers. And now with the situation that have changed, we thought that maybe we should just try to change the medium. So from just reading journal medium, we have gone to this visionary medium to bring the importance of our analysis to everybody. So that's what I had and we had in our mind when we started framing up the contents of this particular course.
Thank you, sir, for giving a brief overview of the content that's released so far. So we got 2 questions from the students on the Google form. I'll just read out the first question, sir. Can you give a real-world example where Lorentz transformation plays a crucial role? There is a question on Lorentz transformation, sir, from a student.
Laws of transformations.
Yes, sir.
Yeah. The transformations, usually when we talk of So we talk of a description, and that description, for some reason or the other, is usually mathematical. To go into slightly more detail of this particular aspect, I would say that if you look at the state of an object, then you can describe it the state of that object with respect to a coordinate system, and you can define it whether it is stationary or it's moving or it is vibrating, pulsating, and things like those. Now, if this particular object that you're talking of is not stationary, and it also does something physical during its existence, that should be detectable to others, those are observing it. The example is, let's say that we look at the stars. The stars, those are sort of stationary. The stars, those are moving towards us, or the stars, those are moving away from us. Now, astronomers all over the world, whenever they have observed some or the other object like this, what they have figured out is apparent color of any particular object can be red shifted or blue shifted or remain as it is. What it means is its frequency may actually seem to be more than what it actually is. We call it blue shifting. There are ones that appear to be less than what it is. We call it red shifted. And the original one, which is as it is, they remain over there. So when you look at the spectrum of a particular line that we're trying to look for, the spectroscopists see the width of the line, how wide is this? And from there, they decide whether this particular object or this source from where the light is coming, whether it is receding away from the observer or moving towards the observer, or it is stationary. So this is one of the examples that I can give before this audience. And the other examples, I think I have narrated them in my lecture, is if you're standing on a railway platform and there is a train that's moving towards you, and the train is actually blowing a horn, then as it moves, one can very clearly experience that the pitch of the sound that's coming is undergoing a modulation. So this particular thing is based on what is usually called the Lorentz group or Lorentz transformation, which plays a very crucial role in the modification of the frequencies that these moving objects are emitting.
Thank you, sir, for giving examples on Lorentz transformation. The next question is from another student. The question is, what is the physical significance of skin depth in electromagnetic wave propagation? What is the physical significance of skin depth in electromagnetic wave propagation?
Yeah, I mean, it has some amount of significance, and that amount can be relatively large to relatively small, depending on the context. Is essentially the fact is we have a skin, all of us probably. And this skin's purpose is very well defined, to protect. When you go to talk of material medium or conductor or something like that, the skin there actually means probably, I mean, I can interpret it the following way, that to what extent the external perturbations can actually go deep inside the conductor. That's the depth. So if the frequency is large, then the depth will vary from what it is when the frequency is small. That's what it is.
Thank you, sir, for explaining about skin depth in electromagnetic wave propagation. The next question is, in what practical applications is controlling ellipticity important? In what practical applications is controlling ellipticity important?
Controlling ellipticity.
Yes, sir.
Well, I mean, in the way we have framed the discussion about the states of polarization, we really didn't want to be innovative and devise a way to control ellipticity. But I guess if someone wants to do that, then for the example that we have talked of in our lecture is propagation of light in a magnetized medium. So what are the things those appear in magnetized medium are as follows. One of them is the magnetic field, whose strength can be manipulated. Density of the material, those are there. And essentially, and you can add to it or take out from it some dipolar substances. So if somebody is interested, they can play around with these parameters and then look at the other side of these apparatus to see how the ellipticity or ellipticity or polarization state of the electromagnetic wave that's coming can be changed.
Thank you, sir, for explaining the importance of ellipticity. The next question is, how are Stokes parameters used in optical communication systems? How are Stokes parameters used in optical communication systems?
See, the Stokes parameters actually are the parameters used to find out the state of the light signal that's being propagated. So some of the parameters that are considered describes the intensity of the light. Some parameters describe the state of linear polarization of the light. The other parameter can describe the degree of polarization, that is circular polarization or elliptic polarization, and get information about the state of the matter that's emitting this radiation. On the other hand, if you want to look into the communication system, then one needs to send some codes through these waves. And these codes better be energy dependent than anything else. I mean, if someone wants to send a code or communicate a code by changing the state of polarization of the light that one is using, my it's a belief, I should say, is it would be rather messy. It would be rather messy because one has to change the state of polarization, and to change the state of polarization, one would need to have a particular medium of certain length, certain temperature, certain number of the other ingredients to change the polarization. So, and the number of times it has to be changed and the way it has to be modulated would make these arrangements bigger and bigger and bigger and bigger. So it is going to be a huge investment in terms of both space, then economy, and time. But on the other hand, if one is actually trying to modulate the wave by modulating its energy, sending one wave on the top of the other, then probably it won't be that messy. It would be more economic in both space-wise and resource-wise.
Thank you, sir, for explaining about Stokes parameters. The next question we received is, what is the difference between radiation produced by linear acceleration and circular motion? So what is the difference between radiation produced by linear acceleration and circular motion?
Okay. If you, this question is, I don't know, what should we call it? Interesting question. The interesting part of it is the gentleman whosoever has asked this question has realized that both have the same origin, that is acceleration. Now, moving in a straight line can be with constant motion. Moving in a straight line can be with acceleration. However, if you're moving in a circle, then it is always acceleration. So we should deduce a conclusion from these two is that a charge or an electrically charged material or a particle, once is subjected to something which is not stationary, should produce radiation. So the next question is, why is it that important? Why does this come into this picture that particles only under acceleration produce radiation? The issue over here is when a particle is subjected to acceleration and it moves certain amount of distance, then because of the acceleration, it must have been acted upon by a force. And because of its motion, it must have traveled some amount of distance in a certain interval of time. So force into acceleration is something like a work done or energy that it has either spent from its own budget or it has acquired. So the one which was stationary or moving with constant velocity, that had a constant energy. But on the other hand, when it's moving under acceleration, it's acquiring energy or it is releasing. Now, depending on the situation, whether it is acquiring energy or it is releasing energy, it is going to radiate. And this is the radiation that you're talking about. Usually, the radiation that is produced by circular motion or elliptic motion is polarized. And to the extent to which circular motion is going to produce a polarized light is going to differ from the extent of polarization that is produced by the charged particle, which is accelerating linearly, may differ. And also the intervening medium in which the charged particle is actually propagating is going to change the degree of polarization. So one can, in principle, look into the degree of polarization of the radiation that's coming out of the charged particle during its motion to decipher the amount of, well, I mean, it's whether it's undergoing linear acceleration or it's circular acceleration.
Thank you, sir, for explaining that doubt. The next question is, why is the velocity of light always lower in a medium than in a vacuum? Why is the velocity of light always lower in a medium than in a vacuum?
Right. Okay. The actual answer or response to this particular question would probably require a rigorous treatment of light propagation and the aspects of electrodynamics. Those are both quantum as well as classical. But let me try to give you here intuitive and empirical answer. You see, what we see when you talk of, I mean, in light is basically a quantum of electromagnetism. So when the quantum of electromagnetism, it propagates in a medium, it comes across or it actually interacts with charged particles, real or virtual. If it is propagating in a medium, then the chance of its interacting with material particles, those are physical, is more than with virtual particles. So what does it do? The photon, being a neutral, it splits itself up into two objects, two particles. One of them is having positively charged particle, and the other one is negatively charged particle. So the total strength is total sum of the electric charge is 0. Now these two charged particles then attract the other charged particles nearby. They interact with them, and then finally they rejoin or recombine at a different point to produce that photon, which resumes its original direction of motion. So it has split itself into two constituents, in between about interacted with others and joined at this point and propagated forward direction to be detected, takes some amount of time. If, I mean, compared to the position situation when it actually didn't interact or with the constituents, those are there surrounding it. So this particular interaction of the photons, constituents, is what finally is responsible for the delay that we see, or rather the reduction in the velocity of the photon when it propagates through a medium. That's a sort of a intuitive and rather empirical answer.
Thank you, sir, for explaining about the velocity of light.
Thank you.
The final question is, how do optical constants influence color perception in different materials?
Uh,
How do optical constants influence color perception in different materials?
Color perception.
Yes, sir.
See, the optical constants, by that we mean what do you call the dielectric constant and permeability, magnetic permeability of a medium. And there is a third optical constant that's usually related to rotation of plane of polarization. Now, this question is rather tricky because in the first place, the concept of perception of color is usually associated with energy. We see a green light to be green, not because someone went and painted it green and said, no, now go. It will be seen as a green light. So or change the dielectric constants. If it's moving, the dielectric constant or permeability, these are sort of inert objects, not very active objects in light propagation. By the word active and passive or inert, I mean they don't impart energy to the light ray that's passing through. On the other hand, if I set that particular light move in the gravitational field of a compact star or something, everywhere the gravitational field is changing. So when it is under motion in such a field, you can think of certain amount of soft energetic particles coming and pumping energy to your photon. So, or if the magnetic or any electromagnetic wave is propagating to a magnetic field that is a function of x, the position, then when it's propagating through such a magnetic field, it is actually taking energy or soft quantas of energy, electromagnetic energy, and that can add on to it. It may not add on to it just like that, because in electrodynamics, photon doesn't interact with itself. But when you take the quantum aspect of it into account, then the soft photons can eventually split into fermion-antifermion pairs. These fermion-antifermion pairs can now interact with your initial beam of light and impart energy to this initial beam of light, and it comes out of the system. So the initial energy of the photons that it started with, because of space-time dependent either gravitational field or non-constant magnetic field, position-dependent electromagnetic field, is pumping energy to the system. So it can change, in principle, the color of the photon that actually started.
Thank you, sir, for explaining about optical constants. So those are all the questions which we received through the Google form, sir. And let me just check on YouTube whether anybody has posted anything. 3 students are watching on YouTube, but they are not posting, sir. They are inactive. And the examination is on 25th of April for this course, sir. Would you like to discuss what questions students expect in the final examination?
Yeah, I think the items that I have told today, even today also, these are the things that one should keep in mind and consider them to prepare for the examination. I don't think there is anything that we have kept which is we have not discussed in this series or few And mostly we have not tried to test the memory of the students. On most occasions, we have tried to see or judge their understanding. So, if the understanding is proper, I don't think any student is really going to face any difficulty.
Okay,
That's
sir.
our
Yeah,
sir.
sure, sir. Sure, sir. So shall we wait for a minute, sir, just in case if somebody...
I'm at your service.
Yeah, definitely, sir. We'll wait for a minute, and in case if they are not posting anything, then we will wind up the session, sir.
I would like to thank you before that for
Sure, sir. Thank you so much, sir. Let's wait for a minute, sir. Meantime, Dr. Ankur Chobe, sir, wants to share something, sir.
I believe Professor Chobe would be more than happy to share his.
So would you like to share something? Yes, sir. Please go ahead, sir. So related to the course, you can share your experience, sir, on the course development as well.
It was my first experience with the SWAYAM team, and I believe that it should be promoted to all over the students of country, and it would definitely help to improve their ability to understand the basic concepts of physics and other branches. It was a good experience. I learned a lot of things from this session, and I hope that I will serve beyond this session. Thank you so much.
Thank you so much, sir. Let me just check one last time whether any question is posted on YouTube. No, sir, nothing is posted. So can we end the session, sir?
I'm thankful to you and NPTEL for giving us the opportunity to communicate things beyond the printed pages so that we can share our views more freely and frequently. Thank you, sir, for conducting it wonderfully.
Thank you so much, sir, for your valuable time. So let's end the session, sir. Thank you, sir.
Thank you, sir.